Yeah. So we would continue our, lectures for that we are doing on in terms of topology, and we will continue today with topology. Only thing is that we will wrap up today with what are the essential things that we have learned today, and from there we will try to get a kind of a conclusion that how things have taken place before we dive into the mathematical part. So, a quick first today, what we will be doing is that we will study and start with this one, which is called orientable and non-orientable surfaces. Now, what I'm trying to tell you is that this orientable and non-orientable surface, which we are learning today, this has got a lot of mathematical implications, right? A lot of mathematics involved into it. But right now, I will just give you a basic kind of an understanding what is a orientable and a non-orientable surface. So right now, what you can see is that you see a torus, right? And then you see a sphere. So what happens is that orientable surface is something which allows a consistent definition of clockwise and counterclockwise. Okay, what do I mean by that? That means if I don't have the kind of a torus right now. So if you get a kind of a torus and you start moving around this one, and then you try to come back to this part, the orientation of your body or the organism or the human body or anything, if you see what is a non-orientable surface, things will become easier. So that will actually create a kind of a same kind of an orientation. That means it won't bend or it won't go anywhere else. So that is why it is called a orientable surface. So here you can see a space is orientable if such a consistent definition exists. So I hope I can make things clear. When you're going around through it, and then when you're coming back, then the body doesn't change. That is what is called a orientable surface. For example, here you can see the typically flat surfaces are all orientable. But even if I take a sphere or if I take a torus, the way we are moving, the orientation when it will come back, that is also the same. Okay, so here you see I don't have the animation, it won't run in StreamYard. So Mobius strip is basically called what is a non-orientable surface. Now the crab which is moving along with that orientable surface is basically the crab around it has left and right flipped, and when it comes out, it would kind of a flip its body. I don't have the animation right now, otherwise I would have shown you. So the directrix through which the body is moving is actually reversed when moved around this path. Okay, so you see a Klein bottle, you see a Mobius snail. So these are actually non-orientable surface. The crab moving around it has left and right flipped with every complete circulation. This won't happen if the crab was moving through a torus. That means if I'm moving through a torus from here to here, you will see that my orientation won't be changed. Just hold on for a second. So that is what is called an orientable surface. In case of a non-orientable surface, the crab, when it is coming back, you will see the entire orientation has changed. And that is what is called a non-orientable surface. Okay, so from here, what we can deduce is this one. Yeah, Vishnu, very good evening. So we can say that an orientable surface is the one where if one moves along the oriented arrow, it is not reversed, and arriving at the point where it started, the directrix is not reversed. And in case a non-orientable surface, the orientable surface is, yeah, Shabir Safi. Good evening. Very good evening. Welcome to this topology. So orientable surface is the one where if one moves along the oriented arrow, it is not reversed. For example, a sphere and a torus. And in a non-orientable surface, for example, a Mobius strip and a Klein bottle, if the body is coming out, then it will be reversed. So this is basically what is called an orientable, non-orientable surface. Right now, maybe it is not that very important to you just to know, but once we do and start with the mathematics, it is very important. So we will once more visit to know what is basically a topological invariant. So here you see, I have shown this maybe earlier also, that when we move along a flat surface to a curved surface, the basic vector is the same. Even if you rotate, one becomes bigger and smaller, yet the vector remains the same. So here is an understanding of what is a topological invariant. So I will explain to you what later is homeomorphism, but let us understand for the time being that homeomorphism is a correspondence between two figures defined by a one-to-one mapping, and that is function is inverse and or continuous. So if I say function which maps from x to y between two topological spaces is homeomorphic or homeomorphism if it has the following properties. That means number one, f should be a bijection, and I've already shown you what is a bijection. First, second is that f has to be continuous and the inverse of that function has to be continuous. So topological invariant, that means, say for example, now if I draw my Jamboard again once here, let me show you. I've got a bad throat. So let me show you. Oh, okay. So I would like to share. Share screen. Okay, so what I'm trying to tell is that if in case that if I'm taking any kind of an object over here, and if I take another object over here, say for example this object, so first of all it has to have a bijection. That means every point which is mentioned over here, right, should have an equal point which is going from here to here, here to here, one-to-one mapping, right? One-to-one mapping. So that is why I have mentioned this one, this particular map, I mean to say the equation as this one. It should be this, right? It should be mapping into this one. And it has to be a bijection. So that is why I showed you this. Now try to understand why this has got a bijection, because again this is a concept of the set. So that means if say for example we assume that there are certain shapes. There is a circle, there is a triangle. Okay, now you see the beauty now, and there is a rectangle. Okay, these are what these are basically what we call, these are polygons. Okay, now we want to, what I told you yesterday and other lectures is that we are trying to get out of the Euclidean polygon and we want to get into a kind of a surface which is very abstract in nature. Now here you see that if I consider this as a kind of a circle, obviously this circle will have small, very small points, right? Say for example this one, it will have many points. Say for example these are the points which are in the circle. Now if I can map all those things into another object, say for example, let us say for the sake of our convenience, let us delete this one and let us draw a kind of an abstract object. Say I draw something like this. Okay, so each point in the triangle, each point in the square, each point in this circle, if it can be mapped to another point, say A, another point, say B, another point, say C, or another point, say D, that means automatically the concept of this object of a polygon is disappearing, isn't it? Are you getting my point? These concepts are disappearing. Rather, what constitutes this particular space is now being mapped through a continuous mapping through from this space to this space. And also the inverse is true. That means from here to here also, if I'm coming back, it would give back to that space. Nicholas, hi everybody. Yeah, Nicholas, warm welcome. I am thankful to your comment. So Nicholas, from where you are logging in, if you can just tell me in the chat box, I would be happy. So the basic concept that I'm trying to explain over here is that why we are taking it as a topological invariant and why it is called a homeomorphism. Why it is called a homeomorphism? Because this would take place between mapping of the function and its continuous. France, okay, great, wow. Let us all greet Mr. Nicholas coming from France. I think that's wonderful. Warm welcome. So, Mr. Nicholas, what I am trying to do is that I'm trying to give everyone an idea of what is a topological invariant, and from there we will wrap up a kind of a summary. So, I hope that this part is clear. That means all those objects that I'm looking over here, I'm trying to get rid of this. I'm trying to get rid of the notion that is a circle, triangle, etc. Rather, I am mapping all those things. So now, let me take this one into the next page. So if I take this one and if I take this one, okay, so that means this particular set, okay, let me explain you to be one particular set. That means this particular set, whatever objects it has got, I'm taking repeatedly polygons. Why? Because this will make you understand. Whatever object it has got, each of them has got a direct bijection to this object. And if this object is a kind of a, I would say, abstract, the inverse should also be true. So f to the power minus 1, that is, from here I can also come back. So I hope this makes things clear, that why, first of all, it makes one thing very clear, that why do we need a set theory in order to know all those things? Number one, because without the set theory, how can we create a bijection? How can we create a one-to-one relation? How can we, I would say, assimilate everything in one group? So that is why we need a set theory. That is one part of the equation. Second part is that if we are going through a continuous homeomorphism, the definition is given over here, that it is one-to-one mapping from the function and its inverse. That means we can get things directly into an abstract object, and thereby we can call it is only topologically invariant if between two topological space is a homeomorphism and it has a bijection, it is continuous, and it is inverse. Inverse is also continuous. So remember, this is a definition we have to visit every day, that what is a topological invariant. So between two topological objects has to have a homeomorphism. One would be a bijection, second would be continuous, and the inverse has to be continuous. Inverse has to be continuous means that inverse cannot be anything discrete, otherwise things will fall. Now here you see in this definition, I have already written that between two topological spaces. That means if I show my Jamboard, this earlier one, this is not a topological space. This is an Euclidean space. So from Euclidean space, how can I move into a topological space? That is a big problem. But the definition here says that it has to be between two topological spaces. So as we will see from there, that is why we need to create the basic foundation. Before anything in topology is dealt with, the first thing that we need to create is what is called a topological space. Here you see homeomorphism is a continuous bending and stretching of an object into a new shape, a correspondence between two figures or surfaces or both geometrical objects defined by a one-to-one mapping which is continuous in both directions. I would say it is a kind of a repetition. Now you see on the right hand side, on the slide, right hand side below, I have actually taken a box just to give you an idea, and I have inflated the box. That means, for example, you're blowing wind in that box. Now you see it continuously deforms, isn't it? I hope I can make things clear. If you're not, if you get this point clear, please do let me know in the chat, in the comment box. So if I blow air and if I inflate that, that is a kind of a continuous deformation, and this ball actually deflates. I would say, sorry, it inflates into a kind of a ball. The square slowly inflates into a kind of a ball, and you see, most importantly, okay, let me take this one. I can show it better over here in the Jamboard. Now if I take this kind of a picture, now you see these have got corners. Okay, I'm drawing those corners. These have got corners. Okay, let me just a second and do a little bit bigger so that you can understand, because I think you're logging in mobile or tab. So if I take this one, this has got corners. All this has got corners. And you see, the moment I try to inflate that, this corner vanishes. And that is why we call it as f is continuous. That is why we are calling this f to be continuous. So what is that? F is basically mapping, f is mapping between x and y. It's a horrible handwriting. I'm so sorry. Let me take this one. That will be easier. That will explain. So f is mapping between x to point y. So if it is mapping, say this one is x and this one is y, then what we see slowly these things disappear. They become very continuous. There are no sharp edges like this. And when I from inflation, if I deflate it and again I'm going back to here, I'm getting back to the original shape. That is why in this type of a definition, I'm so sorry, uh, in this type of a definition, it is written if inverse has to be continuous. It is not that the forward going is continuous and while coming back it becomes discontinuous. No. So sorry. So that is why it shows that the cup, when it goes into a torus and the torus is going to the cup, the inverse is also coming to be true. And the sharp edges are also going out, isn't it? So from here, I will directly take you to the next part, which is this one. So you read this one and I hope it will be clear to you. So you see here that in topology and related mathematics, a topological invariant or topological property is a property that is invariant under homeomorphism. Topological invariants are quantities with topological space that can take on discrete values that do not change under continuous deformation. So that is why this space X can be isomorphic, or we can say topologically invariant to another space A, space B, space C, space D. Because that topological space can take discrete values, that means usually normalized to be integer value. And is there any example of F inverse as not continuous? Yeah, it is a very good question. Let me think over where I think F inverse is not continuous. Uh, let me see, not continuous homeomorphism. I knew this one. I mean to say it was there. I don't remember. But anyway, this is, yeah, I think, yes, yes. Okay, let me show this one to you. We can get this to be done in here, then it will be better. For example, let me show this figure to you. Okay, I hope you can recognize it from here. It's a very good question. So, Nicholas, are you a student of topology? So this one is something which is not continuous. You can see this. I'm so sorry. Yeah. This one won't be continuous. Let me take to the next page. You can see this is called a trefoil knot. Now, why it is not continuous? It was going through continuous deformation over here. And you see it has got, a kind of a thing over here, but it has got an edge. I mean, it's not edge. I mean to say these are crossing over these lines. This one and this is actually what is called, you want enter Euler invariance. No, it is not that Euler invariance. I'm coming to that. This is okay. Oh, I'm so sorry, I have not shown you. Okay, this is something, Nicholas, which has got a kind of a, what you were asking, is there a continuous inverse continuous which is not continuous, and this is what actually happens. This is actually an example which is not continuous. Okay, okay, fine. Yeah, but it is a very good guess. I mean to say, a very good question. Empowering videos, visions, where can I find these notes? Empowering vision, I actually have created the notes all on my own. I mean to say, from this book, from that book, etc. So you won't be able to find it anywhere. You can just watch the videos. I think even you can download the videos. YouTube provides those videos free of cost, right? So this is actually something where we are going, but this is a very good question. I will still try to make it a little bit more precise, with Nicholas' question. I will come back tomorrow explaining a little more on this. But yes, I remember trefoil knot is something which has not got a kind of a F inverse. So that is how it takes place. And a very, very good question. Okay, so here from here, you see, we get to a definition that if a set X is equipped with a kind of a structure, say for example, any structure, and makes X into a topological space, then by a topological invariant of the set X is understood a property of this topological space indeed to the given structure on X. I understand this is a little bit confusing, so just follow the these pictures, how the cup and the homeomorphism is happening, and the box is inflating into a sphere or a soccer ball, and then it is coming back. So that is what, don't worry, we will take into things which are called topologically invariant. We will look into that. This part I don't think I need to explain it again, because this we have already dealt with. And so when the congruency is replaced by topological invariant, we call it a property preserved under homeomorphism. And this is the last one which I mean to show that all these shapes, they are topologically, they are the same, but actually they are, I mean to say, geometrically they are different. So I would like to get a quick kind of a recap of all those things. So before that, I would like to remove this part. And okay, so what I will do is that just quickly, I'm sorry for this, just quickly get over to the first slide, and then I will finally revise on those part, and then I will draw a conclusion to today's class. So what actually, so Nicholas and others who have missed my class earlier lectures, you can just now relax, because so first of all, we understood that why do we need a topology? Because this is something which happened with the evolution of time, that we try to make things easy, gauges become smaller, it become all purpose, and we try to make things portable. Just like the way we want that the computer got generalized, things get smaller, platform independent, just like mobile has got multiple purpose, the television has got multiple purpose. So what we learned from there is that how this torus, cup, and the ball, they can be turned into different kinds of shape. So any shape, any circle, etc. So a circle is topologically equivalent to a square, which is equivalent to a rectangle. But remember that they are geometrically different. So we learned this. And we saw that we are actually, the entire idea of topology was to create any shape, any size, any kind of a form which would be metric independent. Because the moment we try to measure or say that it is a metric, we get confined to a particular kind of a coordinate system. So that is why we saw that topology, let's talk about neighborhoods, closeness, without the notion of distance, because the moment we speak about distance, things become a little bit distorted. So we move from Euclidean to non-Euclidean, from specific to any abstract shape, and that is why we need what is called a topological space. We also learned what is a topology, which is basically from the Greek word topos, which means study, and logy, which is actually, sorry, topos means in subject, and logy, which means definition. So things will stay invariant even if we wrap, etc. So this is actually what is the meaning of topology. And circle is topologically equivalent. Remember, they're geometrically different. The importance of topology we also saw in terms of physics, DNA, robotics, modeling, etc. These are actually geography, I would say geography, GIS system, and many usage. So it has got a widespread usage. The scope of research is huge. It is industry friendly and emerging field of study. There are different branches of topology which we saw: general topology, algebraic geometric topology, which has also got a lower dimension, and differential topology. We saw that algebraic topology has basically got an idea that it takes shape, first shape, and then it takes into shape 2, shape 1, and so on. So it has got distinct values. That means if shape 1 has got a value of 2, that means shape 2 will have a value of 2. But if I assign a different kind of a value, that is 10, then shape 2 is not going to have equal to shape 1 or 2. We also saw what is the difference between differential topology and differential geometry, where entire idea of differential geometry is basically local, something which is very local, and topology is something which is very global on the scale. So we learned what is general topology, and the old name is point topology. And general topology actually normally considers the properties of spaces which are closely related to analysis. We saw how the concepts of the congruence changes, and we don't need any congruency as such, but anything, any shape, and which will be invariant under homeomorphism. The mathematics that we need to learn in topology are primarily number one for set theory. Number two would be a proof-based mathematical system, because every time we need to prove. Why we need to prove? Because this is a new world, this is a new kind of an area where we need to get hold and define each and everything. We also need to understand a little bit of real analysis, and if possible differential geometry. We understood also that from Euclidean space how we move into a topological space, because topological space is a generalization of Euclidean space, because in terms of relationships rather than in terms of distance. That means now we will talk things in terms of relationship rather than distance, d, etc. So there is one kind of a topology which is called a metric space, which is most general, and we try to define the distances using d. But a topological space is a structure which acts in Euclidean, which is generalizes Euclidean space, a space where elements are of a set are called points. So here you see we try to define, there's a definition which satisfies certain conditions, just like an aquatic animal, a cat and a lion. We basically describe them using different definitions. So that is also true. These are examples of different topology. And we saw orientable, non-orientable surface. What is topological invariant? We saw that. And when it is called topological invariant, Nicholas asked a very good question, that if there is any inverse which is not topologically invariant, not smooth, we'll look into that in the next class. I also need to explore. And this is why that they are topologically, they are all the same. So today we end our topology class here only, because the reason is that we are done with the intuitive, geometric and overall understanding of what is topology. I think tomorrow is Sunday. I will be back, maybe not with topology, but something different. But the next class, which we will be dealing on topology, will start with the mathematics of topology. That is first defining what is a topological space. We will look into the mathematical definition. Then we will try to explore and understand the mathematical definition of a topological space. We will take an example, what is a topological space, what is not a topological space. And from there, we will try to prove that if this is the equation, then this is a topological space, and that is not a topological space. From there, we will take our journey further into coarser and finer topology, product topology, box topology, and a lot of things. I think we can have almost a session of a year or so in covering the basics of topology. So thank you. That brings to the end of the intuitive understanding of topology today. Those who have joined new can go back to my first, second, third lecture. This is the fourth lecture which is happening, and have a look onto that. Next time we will be back. Tomorrow also I will be back, but I think I won't be making a video class on topology, but something very interesting. Let us see and look into general relativity or tensors, so that we can understand. Most possibly I will be having a class on tensor. And I am yet to make a routine where I would be explicitly telling you what are the things, what are the further explorations that I'm going to have. Also, the thumbnails needs to be changed in a sequence, and most importantly, I have to put a timestamp, and that is taking a huge amount of time, because each video I have to put a timestamp, so that this part is this part is this, and so on. So thank you very much. Please do subscribe to my channel. Please do share, because I really want everybody to know, learn and learn more, because this is a class which is happening. My Rahat says, thanks, sir. So this is a class which is happening, and I really want to, I'm not boasting, but I really want to make YouTube a very good learning platform. I want to make YouTube something where you can all learn free, absolutely free. And this would be a very sequential way in all the major subjects. Difficult subjects in mathematics and physics will be taken up. There will be classes, a kind of a proper schedule of classes. Oh, you saw the shorts video also. Okay. So thank you very much. You shared also. Okay, so if you don't mind, may I ask you, Myra Rahat? I mean to say, okay, Aparajata. Is this the name of as a male or a female? Don't take me wrong. I'm just asking you, because the Myra, the name itself suggests, maybe because it ends with a vowel, so it might be that it is a woman. So I really cannot understand. So I hope you don't mind asking this question. Aparajita, okay, thank you, sir. Okay, welcome. So we will continue that. And whoever is watching right now, please, spread the news, because as you understand that I am a very small YouTuber. I don't have millions of subscribers, but you people are there. So January onwards, it will be more constructive. And what I request to all of you is that to share amongst your friends, to share among your interested people, to let them know that here is something, a kind of a channel which now takes live classes. And I think Aparajita and everybody will agree that live classes are much more effective than videos. A quick announcement which I forgot is that next Saturday on the 16th of December, starting 7 p.m. Indian Standard Time, I will float a video only. Maria, okay, Maria is my daughter. I am Rahat Pirazda. Okay, okay, mother. Okay, 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 okay. Okay, I am Rahat Pirazda, her daughter. Okay, 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 fine. I got it. Okay. Okay, you are the mother. Okay. Okay, fine. So what I'm trying to tell is that 16th of December, that is next Saturday, a very, very important podcast is going to happen. I'm telling you, it is a very important podcast. And I want none of you to miss. Whether you are in physics or mathematics, doesn't matter. The person's name is Professor Arun Kumar Pati, actually, and he is known to be the father of quantum computation in India. Okay, you sign in from both IDs. Okay. So what is happening is that he is considered to be the father of quantum computer. You can search. Okay, I will just share with you. This is a very I would say I am very fortunate to get this kind of a person on my channel, because his name is not an ordinary name. Uh, Here it is. You can find his name and other details here in Wikipedia. Go ahead and read it, please. Okay. Thank you so much, sir, for your efforts. We will share as much as we can. Thank you very much. So Rachid is logging from Canada, right? Okay. So here is the person who is known to be the father of quantum computation from India. He is the first person who brought quantum computation in India. He is very senior person, Professor Arun Pati. He is coming on my channel on the next Saturday, that is 16, starting from 7 p.m. I want all of you to attend, not for me, but for your, because such a senior person, when he comes, he can speak and, enlighten you a lot. It is not always that you have to have a knack in computer science or quantum computation or quantum supremacy and know what are qubits, etc. But for the sake of knowledge, I think that will be good, isn't it? So I've just given you this chat. In the chat, Arun K. Pati. You can just go and see who is from Triple IT, Secunderabad, etc. So it is all done. I will just float a new video about him, and he will be on 7 o'clock at 7 o'clock next Saturday. I don't want you to miss. Why? Because if you learn, and I will be also learning a lot of things from him, it will be a good experience. He's known to be as the first person who brought in. If you read Wikipedia, you will understand. I don't have to say. Very senior, very learned, very aged person. We can learn a lot. So that is the agenda. I told you after confirmation only I can tell you. 30th also I am trying to bring. But here is another very, 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 very important announcement. That is on the 31st night, because this is generally a party and a New Year night. On the 31st of December, starting 8 p.m. Indian Standard Time, I will be conducting a free webinar on Einstein's general relativity. I know that it is a party time. I know that you will be all going out enjoying with your family, but I will be conducting a webinar on general relativity. It will start from 8 o'clock. It is a very, very, I would say, a detailed webinar. Lot of notes taking, lot of thinking, lot of things will happen on that day. So I will float a kind of a video, but those who are immediately interested, maybe Maida, maybe Rachid, maybe whoever it is, please write an email to me. You already know my email, and just mention your WhatsApp number, okay, and just write it there, your WhatsApp number, and I am interested for the general relativity webinar. This will be conducted via Google Meet. So I will just send you the Google Meet link on 31st morning. Before that, please do register so that I understand, because I have to again make certificates which needs to be given. And this time physics for students is registered under the government of India, small and medium scale industries. You have already seen that. So taken all together, I will do, you are in. Okay. So Nicholas, my email ID is contact, because I will forget, dot physics for students. And this is going to be very intensive. Don't think that it will be a kind of a very easy going, just a kind of a sitting, because there are a lot of, yeah, I have shared this one, contact.physicsforstudents@gmail.com. Please write a mail, Nicholas, so that I can register you and others also. So it would be very intense. I mean to say, you have to really sit down and concentrate, and if you want, you can take notes, because I will be covering a different kind of an aspect of general relativity, a very intensive webinar. I think this is the 5th time that I am conducting it, and I am very happy that if Nicholas from France, because France generally celebrates a huge amount of New Year's, etc. So if you're coming down, I will be very happy. And those also who are watching this live stream, please do write me an email at this email ID. Register your name so that I can understand how many are participating, how many certificates I have to issue, and all those, because I have to make a lot of homework, right? So it will be on 31st, starting 8 p.m. Indian Standard Time. Nicholas, because you are from France, I don't know what will be the time over here. So France time, if I can check in France time now. Oh, it is 5:22 p.m. almost 5:30. So it is now around 6:30, 7:30, 8:30, 9:30. Yeah, around 4.5 hours. I think that is manageable. That means 8 o'clock would be around about 3:34 at your time, right? I saved your WhatsApp number. Fine. So Maida and others who wants to participate, I will also join from Pakistan. Great. So empowering visuals, you have my email ID. Again and again, I'm flashing it on the screen. Yeah, it is currently 7:22. Yeah, absolutely. So I think that it is quite manageable. So empowering vision, if you are joining from Pakistan, I think is just 30-20 minutes. It's not a problem. For overseas people, I keep on reminding, and Indian people think that why Shounak sir is always preferring overseas people. It is not like that, because Indians people know, but people like Nicholas and others who are joining, that would be a problem. So empowering visions from Pakistan, I think half an hour difference manageable. From Lahore also, Maida can join. So do write to me registering, just mention, and do mention your WhatsApp number, because I always send the WhatsApp link via WhatsApp. In case you are not watching the email ID, WhatsApp number is there. So it will be very systematic. Again, I'm telling you 5:22. Yeah. That is what I'm saying. I was wondering why you're telling 7:30. It's 5:22. So that is the thing what I just wanted to tell you, that keep in tab, because it would be wonderful. And I think that a new year with a new kind of a general relativity understanding, and then you step into 2024, it's wonderful. We can also wish each other new year and have a kind of an online virtual party. Yeah, you are from Lahore. So Lahore, I think, is half an hour, right? Empowering vision. So you can. So I won't, want to repeat and repeat and repeat. So do write me an email. It is happening on 31st of December, starting 8 p.m. Indian Standard Time via Google Meet. Send me an email. Tell me a little bit about yourself. Send your WhatsApp number. I will send a confirmation. I will be floating the video tomorrow, mentioning that I'm conducting officially a webinar, but you are all welcome. And for overseas candidates like Nicholas and others who might join, please keep a tab on Indian Standard Time. So anyway, thank you very much. We'll see you tomorrow with a new class, new adventure, new understanding. And yeah, that's it. I'm not wishing you happy Christmas, because we will meet many times before Christmas. And 31st will be equally good, because we will end the general relativity webinar, and then there is a new year. Okay, I think that is the best way. We learn and then we enjoy the new webinar. Thank you very much. Goodbye. Take care. And we'll see you tomorrow. Same time, same channel.